the known universe, size matters. From our vast solar system to the enormous galaxy to the endless expanse of the cosmos.
The enormity is truly unimaginable.
To the tiny molecule and the infinitesimal atoms that make up everything.
The atom is a very tiny unit of matter, and yet they're the fundamental building blocks out of which all matter is made.
From the truly huge to the incomprehensibly small, the universe is a place of extreme sizes.
The universe is actually bigger than we can see.
If you think you know size, you've never seen it like this. Over the next hour, we'll show you why size matters. We'll start with the big and then get even bigger. From the solar system to our Milky Way galaxy to the colossal universe. From there, we'll zero in on the minuscule bits of matter. Molecules and atoms that are the building blocks of everything. We'll show you how they combine and recombine to create every object we see, be it a star, a planet, or even us. In an expanse of such massive size, it's the incomprehensibly small that binds everything together in this great cosmic web we call the universe. Remember that grade school model of the solar system? That styrofoam sun with the 9 dangling planets? Well, that model may have won you a prize at the science fair, but sadly, it was wrong.
The biggest misconception of our solar system, and the one that I explain and re-explain with people, is the relative scales of things. Our solar system is huge.
Our solar system begins with the sun. It's a star that's nearly 900,000 miles across, and around it orbit all the planets.
Well, this is the sort of model solar system you'd find in your typical second grade classroom. It's got the sun in the middle. That's okay, that's correct. Furthermore, you've got them all spaced out here fairly close together so they fit on the stand. But in fact, the distance here are really badly out of proportion.
So how wrong is that little model? How far away would these planets have to be if the sun really was the size of the little red ball? Well, even a football field would have trouble containing them. Let's put our tiny sun at the very back of the end zone. The closest planet to the sun, Mercury, orbits 36 million miles away from our star. But here on the field, that's 8 feet. That means every foot out here on the field is equal to about 4 million miles in space. Venus orbits 67 million miles away in space, 17 feet from our model sun. Earth orbits 93 million miles away from our sun. On the football field, that won't even get us out of the end zone, 22 feet away. Mars has a funny elongated orbit, but on average it's about 140 million miles from the sun. That puts the red planet right about here in our model solar system, on the 2-yard line. And that's it for the small, rocky planets of the inner solar system. Jupiter, the first planet of the outer solar system, orbits here on the 27-yard line. In space, that's 483 million miles. Saturn's another 30 yards downfield, 870 million miles from the sun. Uranus is 1.7 billion miles away from the sun, but here it's in the other end zone, 120 yards away from our little sun. And then finally, there's Neptune, the last planet. It's not even inside the football field. It's 1 billion miles, or 67 yards further out from Uranus, which puts Neptune tailgating in the middle of the parking lot. But what about Pluto? Well, that deserves some explanation, because if there were ever a case of size mattering more, this is it.
When I was a kid, Pluto was a planet. It was a funny planet. Pluto has an elongated orbit and it's tilted from everything else. It didn't make any sense at all. It was just this strange oddball at the edge of the solar system. But it was the only one out there, so no one else knew what to call it.
Pluto's tiny. It's actually smaller than our moon. And for the longest time, it was the only thing we'd seen way out there orbiting the sun. But then, in 2005, Caltech astronomer Mike Brown spotted something else on the far fringes of the solar system.
I was looking at the data that had come down from the night before. I looked at the images and suddenly there it was sitting on the screen.
Whatever it was bigger than Pluto, but twice as far away. Far beyond Mercury, Venus, Earth, and Mars. Past the gas giants, Jupiter, Saturn, Uranus, and Neptune, and 3 billion miles farther out from tiny Pluto. Scientists named it Eris, and its discovery posed an interesting question for astronomers. When it came to planets, did size matter? Because they were both so small, were Eris and Pluto something else altogether? Scientists met in Prague to debate the question and decide Pluto's fate.
The word planet is strictly defined to be a body grounded by self-gravity, which has cleared its orbital zone.
There's more than one criteria for defining a planet.
The recommendation is that we consider Pluto to be in a special class.
After a long and contentious debate, astronomers took a vote.
Those in favor, hold up the yellow card.
In the end, Pluto was voted out of the solar system. Astronomers deemed Eris and Pluto too small to be planets. So they placed them in a special class called dwarf planets.
It was this discovery of this one object bigger than Pluto that led to Pluto being demoted. It wouldn't have happened if I hadn't discovered it.
Might have been better if he hadn't. It turns out Pluto has friends.
I got hate mail at the time. Just last week, I got this very sweet letter from a second grader, handwritten out, that says, "Dear Mr. Brown, I still think Pluto's a planet. Can you please make it one again?" And the answer is, well, no, I can't do it. It's Pluto's own fault, and it deserves its fate.
Recently, astronomers have renamed both Pluto and Eris Plutoids. But as little Pluto found out, size matters in the solar system. And when it comes to size, gargantuan size, nothing in our solar system compares to the Sun. It's hundreds of thousands of times more massive than Mercury, Mars, Venus, and Earth. Even the mightiest planets, Neptune, Uranus, Saturn, and Jupiter, hardly stack up against the Sun in a contest of sheer bulk.
The solar system is the Sun. And more than 99% of the mass of the solar system is there in the Sun.
Our Sun is a star, and it's the biggest object within 24 trillion miles of us. It's so huge that more than 1 million Earths could fit inside it. However, that burning ball of gas shrinks in comparison to some of the truly giant stars out there in the cosmos. From smallest to largest, there's Sirius, Pollux, Arcturus, Rigel, the red giant Betelgeuse, Antares, Mu Cephei, and finally, VV Cephei. But bigger doesn't always mean better. We exist because Earth orbits at just the right distance, 93 million miles away from Earth's star, the Sun. But what would happen if Earth weren't where it was? What if it orbited closer to the Sun, or even farther out? NASA scientist Louise Hanlon has spent a lot of time thinking about just that.
What are the conditions that support human life? In a vast solar system, where is it that a planet might exist that could support life? Well, scientists have a term for this zone. They call it the Goldilocks zone. And this fire here is a good illustration. If I get too close to the fire, I'll burn up. It's too hot. But if I get too far away, in an environment like this, I'll freeze to death. And that's a lot like our solar system. We need to exist in a zone where liquid water flows all the time, where we're neither too close or too far from our star. What most people don't realize is how lucky we are to be on this planet in just the right place for life.
So how different would Earth look if its orbit veered by just a fraction? 5% closer, and searing heat might wipe the surface clean, turning Earth into a blistering desert. 10% farther out, and it could freeze, turning our planet into an icy wasteland covered with glaciers.
Earth is just the right place to have liquid water and to be a habitable planet where life can live.
The point is, we really got lucky. The odds are remote that in a solar system so vast, our planet would be exactly where it needs to be for life to flourish. Our neighborhood of planets seems vast, but compared to the size of our Milky Way galaxy or the universe at large, our solar system is tiny.
When compared with our galaxy and compared with our universe, we are but a tiny, tiny speck on a speck, absolutely minuscule.
Once we travel beyond our solar system, the distances grow so large, counting the miles doesn't even work. So astronomers use a different standard to measure distance, the light year.
The speed of light is 186,000 miles per second, and a light year is the distance that light travels in 1 year.
Traveling 186,000 miles per second, times 60 seconds per minute, times 60 minutes per hour, times 24 hours a day, times 365 days, you travel about 6 trillion miles in that time.
Nearly 6 trillion miles in a year. To put that into context, it means in a year, light could travel around the Earth more than 230 million times. 6 trillion miles is a long way, but the truth is, the light year only makes distances in the cosmos slightly easier to comprehend.
The nearest stars are years away, the nearest galaxies are millions of years away, and the universe is much bigger still.
The distance from our Sun to the farthest planet away, Neptune, is 2.8 billion miles. But the nearest stars are light years away. The Milky Way galaxy is 100,000 light years across. And the universe is much bigger still, spanning tens of billions of light years. Our minds can't conceive of a universe that big. Such colossal size seems beyond the realm of possibility, which is why, for the longest time, we failed to recognize the immensity of the cosmos.
80 years ago, we thought that the entire universe consists of what we know today as our Milky Way galaxy.
Which made sense at the time. Our Milky Way galaxy is a huge place.
Imagine you were standing on one side of the Milky Way galaxy where we live with a very, very bright flashlight, and you switch that flashlight on. It would actually take about 100,000 years for the light to go all the way across the galaxy from one side to the other.
Being so big, it's not surprising we thought our Milky Way was the universe. But we now know that it's only one of about 100 billion other galaxies in the cosmos. So many galaxies, in fact, that if they suddenly turned into peas, they'd fill a sports arena. And in each of these galaxies, there are tens, even hundreds of billions of stars. Altogether, it adds up to a universe with more stars than most of us can imagine.
How vast is space? For an example that might make sense, come to the beach. Think of the grains of sand. And every handful that I pick up, I've got more than 8 million grains of sand. On all of the planet, we think there are 1 quadrillion grains of sand. But it's still nothing compared to space. We know now that there are about 200 billion galaxies, and each galaxy is home to 200 billion stars. So it really is true that space is more vast, with more stars, than there are grains of sand on all the beaches of planet Earth. That's amazing.
And many of these stars are just like our sun. Could an alien form of life be on a planet orbiting one of those stars?
The ancient Greeks looked up and they asked, are there other worlds like ours? Are there planets that may support life like we do?
But for there to be life, there has to be a planet. And up until very recently, we hadn't found a single one outside our solar system.
Back in the 1990s, we hadn't discovered any planets around other stars. We didn't know whether our solar system was some kind of a cosmic quirk.
We now know planets aren't very rare at all. Astronomers have discovered more than 300 planets orbiting other stars. And no one's found more of these so-called extrasolar planets than University of California, Berkeley astronomer Jeff Marcy.
We began discovering the first planets ever around other stars with a trick. You watch the star, and of course a star will be yanked on gravitationally by the planet as the planet goes around that you can't see. And so you'll actually just see the star wobbling.
And the bigger the planet, the bigger the wobble. Astronomers could also tell how fast the planet orbited by the frequency of a star's movement back and forth. The faster a planet orbited, the more the star wobbled. But this method has limits. It can't detect small planets like Earth, only the large ones. And those tend to be gas giants that probably wouldn't harbor life.
So far, our search techniques have only allowed us to detect planets down to about the mass of Neptune or a little smaller. The lower the mass of the planet, the less influence it has on its parent star and the more difficult it is to detect.
Now, astronomers are set to begin the search for small rocky planets like Earth. Scientists think those are the most likely to have the conditions to support life.
A space mission will be launched which will be fully capable of measuring Earth-like planets, and the expectation is we'll find several dozen of these just in the couple years that the satellite is operating.
That mission is Kepler.
The Kepler project is very exciting. It's a telescope which is designed to look for Earth-like planets around sun-like stars.
Packed with ultra-sensitive light detectors, the spacecraft will peer into the cosmos, looking for little worlds like ours.
Essentially, the Kepler spacecraft is a big camera. So what we will be doing is taking a continuous movie of the sky.
Since wobbling stars only allowed us to detect giant planets, Kepler's taking a different approach. It will check for the changes in that star's brightness as a planet crosses and blocks some of the starlight.
If you want to find small planets like Earth, the best way to do it is to look for what happens when a planet passes in front of its star. That reduces the light coming from the star, it gets a bit dimmer, and then when the planet has passed, it gets bright again.
From these tiny variations, scientists will be able to determine the size of the planet and where it orbits its star. From that, researchers will be able to estimate temperatures on the surface of those planets to see whether they have conditions that might support life.
If we do find life, I believe that it begins here today. This is the first step on really understanding who we are and who our family is in the universe.
Few missions have astronomers as excited as Kepler. Though it won't tell us whether we're alone in the universe, it'll definitely give us some idea of where to look for the answer.
Are there planets that may support life like we do? We'll have an answer to that within 5 years.
We'll undoubtedly find lots of these in our local neighborhood. That's less than 0.1% of our galaxy, the Milky Way, and there's 100 billion Milky Ways out there. So the probability of Earth-like planets, and in my view, life on Earth-like planets, is 100%.
Are we alone? It's one of the biggest questions we have about the universe. And for the answer, we're looking up to the stars. But another, even larger question is how the universe came to be in the first place. The answers to that question won't be found in the vastness of space, but in the tiny bits of matter that make up everything. The colossal size of the universe is truly unimaginable. Yet the ironic thing is, every giant object in that endless expanse is made of truly tiny bits of matter. They're called atoms. To get an idea of just how small atoms are, an atom is to an orange as that orange is to the Earth. If we want to understand the very large, we have to look to the very small. Because within each atom are the keys to unlocking some of the universe's greatest mysteries.
The atom is a very tiny unit of matter, and yet they're the fundamental building blocks out of which all matter is made.
I think in order to understand the universe, you really do have to understand the behavior of material on very, very small scale. Atoms and things even smaller than that.
The ancient Greeks were the first to theorize that everything was made up of a single irreducible bit of matter. What they called atomos, we today call atoms. And they're inconceivably small. So small that you'd have to line up a few 100,000 of them before you could see anything.
The human hair is about the thinnest thing you can see. And yet that hair is 300,000 atoms wide. So if the atoms were big enough to see, like this, then in fact the hair would be 10 miles across.
There are many analogies. Like there's 1 billion atoms in the period of a sentence. The point is, there are a lot of atoms in the universe, and they're very small. but they themselves are made up of even smaller particles.
At the center of an atom, at the wee center, is the nucleus. And the nuclei have a combination of particles called protons and particles called neutrons. And out at the edge of the atom, in many layers and many configurations, are electrons.
These particles come together in different numbers to create the elements. The simplest atom, hydrogen, has 1 proton and 1 electron. Double that and add 2 neutrons, and you've got a helium atom. Triple that, and you've got an atom of carbon. And the list goes on, all the way up to the heaviest element here on Earth, plutonium. They're just a few of the 94 elements found on our planet, and they're the building blocks of everything, even life. Inside the average human body, there's 7 octillion atoms. That's a 7 followed by 27 zeros. Considering that, you'd think we'd all know a lot more about them, but we don't. Case in point, the structure of the atom. Most of us think they're pretty compact, with electrons orbiting very close to the nucleus. But just like the popular understanding of our solar system, that's flat out wrong.
If I take this as the nucleus of the atom, typically what you see is little electrons orbiting around like planets orbiting the sun. But in fact, the atom is 99.999999999% empty space.
For a little context on just how much empty space there is inside an atom, here's physics professor James Trefil.
You know, when people first started thinking about the atom, they thought of it as kind of a bowling ball, you know, a solid chunk of stuff. Now, the atom you learned about in school probably looked like this kind of whizzing ball of electricity, you know, and there's a nucleus at the center and the electrons are going in orbit like a miniature solar system. But that's misleading.
If an atom were as large as this cathedral, then the nucleus at the center would only be about the size of a housefly. And the outermost electrons would orbit along the walls. In between, there's nothing. And it's like that for every atom, even the trillions upon trillions of them making up the tissues and organs in each and every one of our bodies.
So that means that the atom is mostly empty space. And that means that the universe is mostly empty space, and that means that you are mostly empty space. But somehow, when these atoms start pushing on each other, they give us the substance of everything we see, and everything we feel, and everything we touch.
So if an atom's mostly empty space, what gives it substance? Why is it that when a batter hits a baseball, the bat doesn't simply pass through the ball? Why don't those particles just slip past one another in the vast nothingness of the atomic world?
Have to remember that the outside of every atom is a layer of electrons. Electrons have a tremendously strong repulsive force. So just imagine your favorite baseball player when he uses a bat to strike a ball. He really didn't hit the ball. He hits the magnetic field of the electrons on the outside of the ball.
That electromagnetic force keeps the bat and the ball from ever touching.
When he hits a home run and he really smacks the ball, when that comes together, it's electrons pushing against electrons.
In fact, this force is at work all the time. It keeps us from ever really touching anything.
When I slap my hands together like that, you think, well, my skin is touching, but actually there's not. There's a little bitty space, because the magnetic repulsion of the electrons on the molecules on the surface of my skin do not allow them to actually touch.
Because they're the components of everything, atoms are fundamental to our understanding of the universe. Yet atoms aren't something we can hold in our hands or see through a microscope. So how do scientists study them and their subatomic structure? With these, they're called particle colliders. They work by speeding particles like protons around in a circle to nearly the speed of light and smashing them into other particles. The collisions create huge amounts of energy and lots of other smaller particles that shoot, twirl, and spin out in all directions. These intricate patterns tell scientists all sorts of things about the subatomic world. It's not unlike smashing a piggy bank with a hammer.
This may look like a piggy bank, but to my eye, it is a nucleus of an atom. There's something inside of that nucleus. I can hear it, but I wonder what it is. Well, I'll do what most scientists do, or try to do, to split a nucleus by shooting a projectile in it. Wow, look what I see. I made a mess, but I can learn a little bit of science from this. You notice that all these coins, they separated themselves by their mass. All the heavy coins are here, quarters and nickels, pennies are here, and look, the dimes are all the way out there. And that phenomena, what we just did with coins, mimics what happens in an atom smasher. When a bullet particle impacts a target particle and the pieces fly off, we can tell the mass of those pieces by how they move from the collision.
These supercharged collisions have helped scientists unravel the secrets of the subatomic world. They showed us that inside every proton and neutron, there were even smaller particles, called quarks, which scientists now believe were the only thing in existence at the very beginning of the universe. But the work done in these colliders isn't all about unraveling the mysteries of the universe. The insights gleaned from these collisions have spawned new technologies like CAT scans and PET scans that allow doctors to look inside the body to diagnose and treat disease. They've also helped researchers learn how to manipulate the atom to create structures and substances that could revolutionize the world we live in. The atom is the basic building block of the universe. They are, quite literally, at the heart of everything. So understanding them means understanding the cosmos and the world in which we live. The particles in atoms, those protons, neutrons, and electrons, come together in different numbers to give us atoms with unique chemical properties. We call those various atoms elements. There are 94 elements found here on Earth. And they come together in some astounding ways to create molecules. From the marriage of a volatile solid, sodium, and a poisonous gas, chlorine, we get salt. Two of nature's most flammable substances, the elements hydrogen and oxygen, combine rather ironically to create the world's best fire extinguisher, water. The elements combine to form molecules, which then go on to create everything we see, smell, touch, and taste. But to understand how we get such a variety of substances from such a small number of elements, it's helpful to think of a library and what it is that makes a library a library.
You know, the universe is a pretty complicated place. You got atoms coming together to make molecules. You got molecules making all the stuff you see around you. It's complicated, but there's an easy way to think about it. You can think about it like a library. So what is a library anyway? How do you build one? What's the fundamental building block you need to put a library together? Now you ask most people that question, they're going to say books. But it's not that simple. There's a whole lot more to it than that. You can see why it's so complicated just by opening a book. When you do that, you see the book is made out of words. And every book in this library is made out of those same words in different combinations. And then you look at the words and you see they're made out of letters, 26 in the English alphabet. So what's the basic building block of the library? It's the letter. And from the letter you make the words, and from the words you make the sentences, and from the sentences you make the books, and from the books you make the library. The universe is like that too. Like the library, it's made from fundamental building blocks. Everything you see around you is made from molecules. Molecules are made from atoms. Atoms are made from elementary particles, and elementary particles are made from things smaller still. But no matter how far we go in this quest, these are the things that make up the universe we live in.
For centuries, we've known how to combine elements to make substances like bronze, steel, and plastic. But we're now entering an age where scientists are able to work on the atomic level to manipulate atoms and molecules to create new tools that promise to revolutionize the world we live in. Welcome to the world of nanotechnology.
A nanometer is 1/billionth the size of a meter, which is about this big. Our fingernail grows 1 nanometer every second. By the time I finish this sentence, my fingernail will have grown 5 nanometers.
So it's working at this tiny scale that's opened the door to a whole new world. Nanotechnology is expected to deliver all sorts of improvements to our daily lives. From ultra-strong, ultra-light building materials to stain-repellent pants. But nowhere is nanotechnology expected to have a bigger impact than in medicine. As a medical researcher, Dr. Dean Ho has been looking into nanodiamonds to take the place of syringes and pills to treat disease.
My group develops nanodiamonds, essentially diamonds, particles that are at the nanoscale. They're about 4 to 5 nanometers per diamond for applications in therapeutics and drug delivery.
Dr. Ho and his team of researchers are looking at these diamonds as a way to treat cancer. The process works by assembling a group of diamonds and then coating them with the cancer-killing drug. The diamonds are then studded with protein receptors. Once in the bloodstream, the nanodiamonds skip over the healthy tissues until they find the cancer cell.
The Y-shaped proteins on the nanodiamonds fit more effectively with the triangular-shaped proteins on the tumor cells. The nanodiamonds are then taken into the cancer cells and into the tumor itself, where then the drug can then be released and the tumor is then killed.
Using these nanodiamonds to target cancer cells could result in vastly improved treatment while cutting down on the harmful side effects of traditional chemotherapy.
One issue right now that confronts oncologists that prevents them from optimizing their treatment is that patients continually have to be injected with chemotherapy. And these chemotherapies are very harmful to the healthy tissue of the body.
Chemotherapy doesn't distinguish between cancer cells and healthy cells. It attacks both and results in sometimes debilitating side effects for patients.
If we can think about loading these drugs onto nanomaterials, we can think about circulating them in the body for a longer period of time. And in so doing, we don't have to continually inject these patients over and over and over again. So we get a higher efficiency of treatment per injection with these nanomaterials and drugs. And what that means for the patient is reduced side effects based upon the power of nanotechnology. Right now is a very exciting time to be at the forefront of nanotechnology. And the reason for that is because several disciplines are coming together to create novel functions based upon nanotechnology. And some examples include clinicians working together with engineers, working together with scientists to create novel technologies that what many people think will transform how medicine is practiced.
Though it may sound like it's straight out of science fiction, nanotechnology has been around longer than we have. Nature's been working at the nanoscale since the dawn of life. And it's nature that's given researchers all sorts of ideas. Take this water-repellent leaf. It's inspired scientists to build a better pair of pants.
We're using nanotechnology to deliver enhancements to fabric.
William Ware and his team have created a pair of pants that will fend off just about anything that can be sprayed, poured, spilled, or splattered.
Here I have two pieces of 100% cotton fabric, just native cotton fabric, and as you can see, it's highly absorbent. This is just water. We use conventional textile processing equipment, and we apply our technology to fabric, and this is our technology. This is where the magic happens.
Ware uses complex molecules called polymers to coat the fabric with tiny nanohairs that will repel just about any liquid.
So it's come in contact with the technology. This is just squeezing out the excess liquid on the fabric. Now I'm going to take this and put it in the oven to cause the polymer to permanently attach to the fiber surface. So it goes into the oven for a predetermined amount of time, generally about a minute, and when it comes out, it's done. Controlling the temperature on the fabric is very important. The technology needs a certain amount of energy for it to attach to the fiber surface. This oven is designed so it can monitor the fabric temperature and determine when the fabric is essentially done with the binding process. It's done. Same piece of cotton fabric. Nanotechnology at work.
What we have here are some regular 100% wool pants, what you would find in any store. The difference is they contain resist spills, repellency technology. You can't see it, you can't touch it, you don't know that it's there until you drop liquids on it. You can see that the liquid just beads up, can move around on the fabric, doesn't penetrate the fibers of the fabric, and then it'll just roll right off. So whether it's a coffee spill, whether you're out in inclement weather, it won't penetrate the fabric and it stays looking nice and fresh.
So how does it work? The coating implants tiny nano whiskers that actually suspend the liquid above the fabric and never touches it. Many unknowns remain in the world of nanotechnology, but the ability to work at the atomic scale has the potential to change the way we live. If there's one thing the universe excels at, it's recycling. All the matter in the cosmos was created when the universe was born, 13.7 billion years ago. And since then, not a single atom has been created nor destroyed. They've all just been quietly combining and recombining in an endless cycle of creation. At some point in the far distant past, we were dealt a pretty good hand when an ancient star died a spectacular death and seeded our little corner of the galaxy with everything we'd ever need. All the raw materials, all the iron, carbon, calcium, oxygen, and other elements that would billions of years later lead to this: life.
The universe is the ultimate recycling machine. Almost every atom that's in your body began life in a star.
Every atom in every one of us was at some point part of a star. In fact, everything around us was once part of a star. Those stars forged all the heavier elements that would much later come together to create the molecules that form everything we see, even us.
We're all recycled atoms. It's absolutely true.
We see the same kind of recycling here on Earth. The atoms that formed the planet have been reused to create and sustain every organism that ever lived.
When you take a glass of water and you drink those oxygen atoms, really what you're drinking is the remnants of a star explosion. And of course, since those oxygen atoms came to Earth, they've been recycled a good deal too. So you're also drinking bits of dinosaurs and bits of all the famous people you've ever heard of.
Each time you take a breath, quadrillions of atoms enter your lungs. These atoms have been mixed throughout the Earth's atmosphere over time, but they're the same nitrogen and oxygen atoms that were there. So each time you breathe in, you're breathing in a couple atoms that Galileo breathed out, or that Copernicus breathed out, or that Socrates breathed out 500 or 2,000 years ago.
Each one of the trillions upon trillions of atoms in us began their journey inside a star. Since then, they've made countless stops in mountains and rivers, in trees and blades of grass, in molds and mushrooms, in deer, daffodils, and dinosaurs. And when those atoms are done with us, they'll go on to recombine with something else. That's how it's been since the beginning. A continual process of creation and recreation. The universe is a place dominated by extreme sizes. And while it seems the massive and the minute are separated by unimaginable differences, they're actually more similar than you may think.
Something I find intriguing as a scientist is that the structure of the very, very large looks very much like the structure of the very, very small. Looking inside those atoms, they begin to look a bit like the universe.
It's the size of things in the universe that make it such a puzzle. And it's only by looking at the very big and the very small that we can piece together answers about how the universe came to exist and why it evolved into something that would include us.
People who are looking at the biggest thing you can think about, the universe, and people who are looking at the littlest thing you can think about, they're really talking about the same thing.
Whether peering into a telescope or looking down into a microscope, scientists are looking for answers to the same question. How did we get here? The secrets of life are hidden in a maze of extreme sizes, leaving us with much to learn about the known universe. $13.7 billion years ago, our universe started with a colossal explosion called the Big Bang. That powerful blast created all the matter in the universe and laid the groundwork for every explosion since. From fiery volcanic blasts to cataclysmic asteroid impacts to exploding stars, nature's most destructive powers were born in that single instant. We'll start with the explosions we know: gunpowder and nuclear detonations. And then take you out into the cosmos to witness explosions of a different magnitude altogether. So what is an explosion? Well, it's energy, a sudden and often violent release of energy. But here on Earth and in the cosmos, this violent release doesn't have to come from the largest objects. It's often the very small things that create the biggest explosions.
Black powder looks fairly benign, but stored within its molecular bonds is an incredible amount of chemical energy.
Chemical energy is a form of energy that comes from the forces of attraction that hold atoms and other particles together in molecules. In water, for example, hydrogen and oxygen atoms are joined together by strong forces called chemical bonds. When those bonds are broken, chemical energy is released.
It required a lot of chemical energy to create those bonds, and now that we break those bonds, that energy will be released. 2, 3, go! Oh. Boom, that's the way to do it. What we're going to do is take that 250-pound anvil, place it on top of this one, ignite the black powder, and see how high it goes. So it's all wired up, ready to go?
All ready to go.
Okay, Bob. 3.
Fire in the hole.
Fire in the hole, I'm ready. 2, 1. Wow, man.
Good job, man, good job. Thank you, thank you.
Setting fire to a few ounces of black powder shot a 250-pound anvil 50 feet into the air. That's an example of the energy set loose when you break a chemical bond. Break a nuclear bond, those bonds that tie the protons and neutrons inside the atom together, and the energy released is enormous. The largest nuclear weapon we've ever detonated had the power of 50 megatons of TNT. Yet the explosions we create are nothing when compared to the raw power of Mother Nature. The 2004 quake in Indonesia that spawned that devastating tsunami had the energy of 100 gigatons of TNT. That's the equivalent of 2,000 of our biggest nuclear bombs. Volcanoes, earthquakes, hurricanes, and tsunamis can wreak havoc over huge areas. But even our mightiest natural disasters on Earth don't have the destructive power of cosmic impacts.
Every 100 million years, everything on Earth that weighs more than 25 kilograms dies. That's more than 50 pounds.
What kills these animals are space rocks, the cosmic leftovers of when our solar system formed nearly 5 billion years ago. Asteroids and hulking balls of ice that are hurtling through space at tens of thousands of miles an hour. And And scientists think it was an asteroid the size of Manhattan that wiped out the dinosaurs 65 million years ago.
When the dinosaur-killing meteorite arrived, the energy that the impact brought in is huge in comparison to anything else the human race has done. 2 million times larger than the biggest nuclear weapon ever detonated.
How could an object only 6 miles in diameter wreak such havoc on the entire planet? To understand the devastation of a large meteor impact, let's start smaller, with a rock the size of a house, and the crater it left behind when it slammed into the Arizona desert 50,000 years ago.
This is Meteor Crater. The first time I came to this place, it took my breath away. It's so huge. It gives you just the idea of how much power it takes to form something this big.
Planetary scientist Elisabetta Pirazzo is an expert on the asteroid that left a gaping hole nearly 3/4 of a mile across.
It's astounding to think that a body that is only 150 feet in diameter can create a crater this big.
This meteor was traveling over 26,000 miles an hour. That's 10 times faster than a bullet. When it struck the ground, it gouged out more than 175 million tons of rock and flung it tens of thousands of feet into the atmosphere.
The energy that was necessary to open this crater is of the order of 10 to 20 megatons.
20 megatons. That's 1,000 times more powerful than the atom bomb that devastated Hiroshima. Now, imagine an asteroid 200 times bigger striking Earth, with a blast equal to 100 million megatons. That's what scientists believe killed the dinosaurs 65 million years ago. And it could happen again. So what if it did? What if an asteroid that big headed straight for a city like Las Vegas? The first hint of the impact is a blinding flash. Then, the sound.
When an asteroid or a meteor comes into the Earth's atmosphere, it creates an enormous shockwave.
The shockwave, a deafening blast.
It won't be slowed down by the atmosphere, but the surface will be heated to incandescence. It'll be extremely bright, extremely hot.
What follows is an apocalypse. As the space rock plunges through the atmosphere, it compresses and heats the air beneath to thousands of degrees. It sends out an air blast at 9,000 miles an hour. The fiery wave incinerates everything within 200 miles. Then there's the impact. In a fraction of a second, the asteroid vaporizes hundreds of millions of tons of rock. The western United States shudders as an earthquake measuring more than 9.7 on the Richter scale levels cities and towns hundreds of miles away from the impact site. As the shaking rages, cities like Denver, San Francisco, and Los Angeles are wiped from the landscape by another wave of superheated rock and debris. When the smoke clears, what's left is a 70-mile-wide crater and a devastated landscape stretching thousands of miles in every direction. The debris that didn't rain down on nearby cities fans across the atmosphere to block out the sun. In the weeks and months that follow, the extinctions begin. Plants are the first to go. Without enough sunlight, they wither and die. Plant-eating animals starve. And after that, one after another, animals farther up the food chain, even us, can't find enough food to keep themselves alive. The devastating energy of cosmic impacts is almost unimaginable. But these impacts shaped our planet in the past and will have dramatic effects on life in the future. If a giant asteroid plowed into our planet, it would have devastating effects. The explosive power of a cosmic impact could be enough to wipe out civilization. But what are the odds we'll get hit by one of these cosmic killers anytime soon?
We've been bombarded by about 30 to 40,000 tons of material per year. People would see this normally with shooting stars.
Every day, the Earth is pelted with 25 tons of dust and sand-sized particles, but they burn up in our atmosphere. About once a year, an automobile-sized asteroid hits Earth's atmosphere, creates a blazing fireball, but burns up before it touches ground. Every 1,000 years, an object the size of the Statue of Liberty hits Earth and causes significant damage. That's about twice the size of the asteroid that created Arizona's meteor crater. And every few million years, an object as big as a mountain comes along and threatens life on our planet. Government agencies like NASA are hard at work trying to track near-Earth objects. But even if we spotted one of these objects headed our way, is there anything we could do about it? A nuclear bomb might not have enough power to deflect an asteroid. And blowing it up might mean several large meteors hitting Earth instead of just one. But University of Arizona planetary scientist Jay Malash thinks that if it ever came to saving Earth from just such a catastrophe, our sun might be used to protect us.
Our idea is to collect sunlight with a big parabolic mirror. Focus it down to the asteroid surface. The heat from the sun focuses on the asteroid, heats the surface up to the point where it starts to vaporize, and that expanding vapor forms essentially a crude rocket that pushes the asteroid in the opposite direction.
But is sunlight really powerful enough to deflect an asteroid? Well, at the Sandia National Laboratory in New Mexico, they're already testing to see just how much of a punch concentrated sunlight packs.
We think of the sunlight as a dispersed source of energy. It's not real hot, we can stand out in it. But when we take all these mirrors and focus that light to a point, you get a light that's more intense than anything that we can make with electricity or other power sources.
Chuck Andraka knows concentrated sunlight packs a mighty punch and could be enough to deflect an incoming asteroid. These mirrors focus beams of light to a single point inside the tower, with the power equivalent to 7,000 suns. The temperature of these focused beams can reach tens of thousands of degrees.
And that's enough energy in one small place, about that big around, that we can melt anything known to man.
Like a steel plate.
Okay, we're ready. Okay. Oh, we got a nice puddle up here. Still glowing orange, look at that.
Oh yeah.
When it comes to deflecting massive asteroids on a collision course with Earth, the Sun may be our best bet. It is, after all, an object of staggering power that in 1 second creates millions of times more energy than has ever been created on Earth.
The amount of energy the sun produces per second is the equivalent of about 2 billion 100 megaton H-bombs.
Our sun was born some 5 billion years ago, when a colossal cloud of hydrogen began to pool together.
Gravity pulls it together, and it falls together, and it falls together and heats up, and if there's enough of it, it gets hot enough to start nuclear fusion. You'll get to 10 million degrees. At 10 million degrees, it doesn't matter Fahrenheit, Celsius. It's 10 million degrees. It's really hot.
When it gets to a temperature in its core that's sufficient to take hydrogen atoms and stick them together to make helium atoms, the nuclear reaction can turn on.
That nuclear reaction is called fusion. Normally, the positive electric charge of protons at the center of the atom repel one another. But in the core of the sun, where the temperatures and pressures are so immense, they can be stuck together. And when that happens, vast amounts of energy are created. Just a couple hundred years ago, Earth's finest minds thought the sun was a hot lump of coal. Even now, a lot of us think the sun's a solid sphere, burning hot like an ember out in space. But the sun's a very dynamic place, and not at all what we thought of in the past.
The most common misconception about the sun probably is that it's very dependable, so that people just take it for granted. But of course we know the sun changes, and we have to learn about how the sun works because it does affect us on Earth.
If you want to study the sun, this is where you go. Kitt Peak, just outside of Tucson, Arizona.
This is a McMath Pierce solar telescope. It was designed and built in the early 60s. It's still the largest solar telescope in the world.
NASA astrophysicist Don Jennings uses this telescope to study our sun.
The surface of the sun that we see has granulation caused by this turbulence coming up from underneath. And so you have structures that change all the time.
This violent, ever-changing surface hints at the colossal powers at work deep inside the sun.
If you could take the sun and slice it and look at the interior, you would see a very hot core.
The core is the engine of the sun, with a temperature of 27 million degrees Fahrenheit. Gravity is trying to shrink the star, so there's immense pressure at the core, hundreds of billions of times greater than here on Earth. All of the sun's light and energy is born in this nuclear furnace. Here in the center, the pressures are so great and the matter so tightly compact, a particle of light can spend 1 million years trying to find its way out of the core and up to the sun's bubbling surface, where it zooms off into space. 8 minutes later, some of that light hits us here on Earth. We rely on some of that light to make electricity to power our homes and businesses. But what if we could harness that same process of fusion that created that light?
Fusion in the sun is done with hydrogen, and were we to do it on Earth, we do it in the same way. The entire energy needs of the United States could be supplied by 7 ounces of water being used up each second.
Fusion is a very efficient process that uses hydrogen, the same kind of hydrogen found in a molecule of water, to fuel it. Fuse together 2 atoms of hydrogen, and you release a tremendous amount of energy. Bind all of the hydrogen atoms in a small lake together, and you could power the world.
So if you had a reservoir that was, say, a mile across and 50 feet deep, it would supply the world's energy supply for the next 150 years.
Is that possible? Astrophysics professor Rob Goldston and his group at the Princeton Plasma Laboratory think it might be.
We are producing megawatts, millions of watts of fusion power in our current experiments, and we are measuring it in great detail. We know that we're now producing fusion power.
Goldston's reactor uses the same fuel as the sun, hydrogen plasma, or superheated hydrogen gas. But the sun's got a huge advantage. Its immense gravity can squeeze atoms together to get them to fuse. So, to compensate, Goldston's turned up the heat to 100 million degrees Celsius. At those temperatures, the atoms are moving so fast that when they collide, they fuse.
The core of the sun is actually 10 times cooler than the plasmas we make, but much, much denser, much heavier, much more gas there than in our experiments. A lot of people wonder, here I've got a plasma that's at 100 million degrees centigrade, how come everything isn't melting?
There's no substance in the world that can hold something that hot. So to contain the plasma, Goldston uses magnets.
Instead of using gravity in our systems, we use magnetic fields. A plasma is made up of plus charges and minus charges. A magnetic field is very, very effective for holding on to this kind of plasma. The pluses and the minuses spiral along the magnetic field. So if I connect the magnetic field up in a circle, this very, very hot gas that you might think would go everywhere, in fact, will just spiral around the magnetic field like beads on a string. And then the plus charges can slam into each other and give you fusion.
But only for an instant. So far, Goldston's been able to achieve fusion for only a second. That's a far cry from what the sun's been doing for 5 billion years and will continue to do for 5 billion more. The sun's power is vast, and the nuclear process responsible for it not only nourishes Earth, but has the potential to save it from catastrophe. Whether it's powering our homes or running interference on incoming space rocks, the sun is both nurturer and protector. The force of a massive quake. The impact of a giant asteroid. The awesome power of our sun. Each is an epic example of the raw power in the universe. Yet every one of them pales in comparison to the forces unleashed during the explosive death of stars. Once a century, in galaxies the size of our Milky Way, a star blows itself to smithereens in some of the most enormous explosions ever witnessed. They're called supernovas.
By far the most powerful events that occur in the universe today are supernovae. They produce, in a fraction of a second, 300 times as much energy as the sun will produce over its 10 billion year lifetime.
Supernovas only occur in stars that are at least 8 times more massive than our sun. Having exhausted their supply of nuclear fuel, these giant stars undergo a rapid and violent collapse.
The matter of the star, the mass of the star, falls in very rapidly at speeds approaching the speed of light, at which point there's an explosion, which is the supernova explosion, and the material is propelled outward at tremendous speeds.
The flash from a supernova is so bright, it outshines every other star in the galaxy.
We can see supernova in other galaxies for a 2-week period in which the supernova itself outshines the light from all of the stars in the galaxy.
If such an explosion occurred somewhere near Earth, it would be like having another sun in our sky. And if a star any closer than a few hundred light years went supernova, we'd see more than just a light show. The cosmic blast could wreak havoc here on Earth.
The energy released in the supernova could interact with the atmosphere, destroying the ozone layer, stripping the Earth of its protective shield to ultraviolet radiation and cosmic rays. And there could be, in principle, a catastrophic extinction here on Earth.
So is there any chance of this happening? Are there any stars close enough to us that might soon blow themselves to bits and rain destruction down on planet Earth? Thankfully, the answer is no. The closest star that may go supernova is in the Spica system, and it's 260 light-years away. Far enough where it wouldn't harm life on our planet if it went supernova. Supernovas only happen in huge stars, stars many times more massive than our Sun. Yet our Sun will one day run out of fuel. And even though it won't explode, the Sun's death won't be any less destructive.
Oh, our Sun, our poor Sun. The Sun will eventually run out of hydrogen to burn.
5 billion years from now, the Sun will run out of fuel. When that happens, the Sun's core will collapse. The immense pressure will force the core's temperature up to 100 million degrees, at which point it begins fusing helium into carbon. The heat radiating out causes the Sun's outer layers to swell.
The Sun will then go through a phase we call a red giant phase.
It will swell to the point where it swallows Mercury, then swallows Venus, and probably, and it's right about on the edge here, probably swallows the Earth.
Finally, when there's no more helium to fuse, the nuclear furnace shuts off.
The core just locks up and stops, and then the Sun is officially dead. It is no longer generating nuclear energy. It is no longer a live star.
Now dead, the swollen outer layers of the Sun drift off into space in brilliant curtains of hot, glowing gas.
The outer envelope will just continue to expand and form what we call planetary nebula. That's how a star like our Sun recycles a part of what made it up during life back into the universe to form the next generation of stars.
And what's left of our Sun is just a small glowing ember of carbon.
It's just gonna collapse down to a hot white cinder called a white dwarf. And this will be a star the mass of the Sun and the size of the Earth.
The death of stars are some of the most powerful events in the universe. Whether stars collapse into white dwarfs like our Sun, or explode in brilliant supernovae that can be seen clear across the cosmos, they are potent reminders of the powerful forces at work in the universe. The death of stars are some of the most powerful events in our universe. Even on the vast cosmic stage, these explosions are epic events, so enormous, we see their light from billions of light years away. Yet the visible light we see from supernovas are just a small portion of the total energies coming from these enormous blasts. The rest is emitted as radiation our eyes aren't engineered to see. The human eye is tuned in to just a very narrow band of the electromagnetic spectrum. In fact, what we can see is just a tiny fraction of all the light on the spectrum.
The only thing that distinguishes one part of the spectrum from the other is the wavelength. They have a different energy, but all of the properties are the same.
If we could turn a dial on our eyes, we could see lower frequency wavelengths, like radio waves, microwaves, and infrared. Turn it up and we could see the higher frequencies, like ultraviolet, X-rays, and gamma rays. And looking at the world in these other frequencies, we see that everything around us emits light.
So a kind of cool thing about matter that people don't necessarily understand is that everything is emitting light. We emit light, you're just not emitting it in the part that our eyes can see. And our bodies are actually warm to the touch, and as a result, they're actually also emitting infrared light.
This camera is showing you my image in infrared. The hot places on my body are giving off infrared, like my throat and my forehead. But my glasses are colder than my body, and they do not give off infrared. They look dark. Hot objects emit a lot of energy. You've got hot water and cold water. You can see the warmer gives off radiation.
More energy means higher frequency, and the highest frequency radiation is something called a gamma ray. Gamma rays are deadly. They pack so much power, they can break molecular bonds.
It can potentially cause cancer in a cell by doing enough damage to the tissue that you've destroyed something.
And when we go looking for this deadly radiation, we see it streaming from the most powerful explosions in the universe. Gamma ray bursts.
Gamma ray bursts are the most spectacular events that we know of, and the brightest events in the universe since the Big Bang occurred.
Gamma ray bursts are produced by colossal supernovas. They're billions upon billions of times brighter than our sun. They shine so intensely, they make our sun seem dark by comparison.
To get an idea of how incredibly bright a gamma ray burst is, I'm going to represent the brightness of our sun by this match. And then the gamma ray burst we can represent by the World War II searchlight behind me. It's incredibly bright, but in fact not nearly bright enough. And we would need 1,000,000 trillion such searchlights to accurately represent the gamma ray burst.
These bursts usually come from galaxies billions of light years from our own, so distant that by the time this deadly radiation reaches Earth, it's too weak to do any harm. But if a gamma ray burst were to occur closer to Earth, it would be a different story.
If one of these gamma ray bursts weren't to happen in a distant galaxy, but very nearby in our Milky Way, this could potentially be something that would devastate life on Earth. Some pretty nasty things would happen. I mean, we're now no longer talking about just a few gamma rays here and there. We're talking about being bathed in a wash of gamma rays.
If gamma ray radiation from a burst within 6,000 light years hit Earth's atmosphere, it could destroy our protective ozone layer. the ultraviolet radiation from our sun would filter through our atmosphere, killing much of the life on land and near the surface of oceans and lakes. We'd see rapid changes in climate. We'd be bathed in massive amounts of acid rain, and ultimately we'd see mass extinctions in every corner of the globe. So what are the odds of a gamma-ray burst happening within a few thousand light years of Earth? Turns out, pretty remote.
Luckily, we believe these gamma-ray bursters are quite rare out there in the distant reaches of the universe.
Scientists estimate there's about 0.1% chance of a gamma-ray burst occurring in our galaxy. And even then, the explosion would have to happen within 6,000 light years of Earth, which is pretty close, considering our galaxy is 100,000 light years across. The universe is not the serenely beautiful place we see with our eyes. Hidden from our view are powerful forces that reveal ever-present dangers. From supernovas to gamma-ray bursts, the universe is above all a place of explosive extremes. There are powerful forces at work in the universe. From man-made explosions to Mother Nature's devastating destruction, to epic blasts of unbelievable cosmic power. All of them reveal a universe of lurking perils, like exploding stars, apocalyptic asteroid impacts, and invisible jets of radiation streaming across the universe. The cosmos is a place of ever-present danger. But what's amazing is that in the entire universe, nothing is more powerful than the colossal explosion that created it all, the Big Bang.
The Big Bang is an amazingly difficult thing to wrap your brain around, which isn't surprising. When you're trying to think about the universe being smaller than the head of a pin,
actually smaller than an atom, about as small as the proton at the center of an atom. Whatever the universe was at the very beginning, some 13.7 billion years ago, we think it was tiny, an infinitesimal nugget of space. And then something happened, triggering the most colossal explosion in history. In a billionth of a billionth of a billionth of a second, the universe grew from the size of that tiny point to something billions of miles across. This colossal blast created everything, all the matter we see in the universe today. And it did all this without even making a sound.
When one sees the Big Bang portrayed in a film, there's always a big bang, a noise. Of course, that's silly because sound doesn't propagate in space. But what's often overlooked is that the Big Bang is not just an explosion that happened at some moment in time at some point in space.
it was not just an explosion of material into an empty universe that was sitting there waiting to be filled. It was the explosion of space and time into existence to begin with.
And that's what trips most of us up. Before the Big Bang, there was nothing, literally nothing. And the black void of space is something. So is time.
To ask what's before the Big Bang, what's before there is time, is really a meaningless question. And likewise, to ask where the Big Bang occurred is meaningless because there was no space.
300,000 years after the Big Bang, the first atoms formed. 200 million years later, the first stars are born. And 500 million years later, the first galaxies, including our own Milky Way, begin to form. The Big Bang powered the expansion of space, and all the matter, including every galaxy, got dragged along with it. A balloon works as a good analogy. The surface of the balloon represents the universe. Each red dot on the balloon is a galaxy, and the blowing up of the balloon represents the expansion of the universe. As the universe expands, the space between each galaxy increases, driving them farther and farther apart from one another.
No matter which little dot we sit on, every other dot is running away from us. The farther away we look, the farther dots are running away from us faster. And in fact, there may be some dots that are running away so fast that they go over the edge and we can't see them anymore.
For decades, we've known the universe is growing in size. But scientists had assumed that gravity, the force that attracts and pulls objects toward one another, would eventually stop that expansion and cause the cosmos to fall in on itself in something called the Big Crunch. But then, in 1998, scientists made a shocking discovery.
We discovered that the universe wasn't slowing down, it was speeding up. And at that point, you suddenly realize, gravity doesn't explain this anymore.
But what did explain it? What immense power fuels this accelerated expansion?
We don't have the slightest idea what serves to expand the space between the galaxies. It's one of the great puzzles in modern science.
It flew in the face of everything we knew and understood about nature. So like a sinister villain in a comic book, astronomers gave it the name dark energy.
The whole concept of dark energy is really pretty bizarre, almost flying in the face of physics as we understand it. When we look at the expanding universe, we would expect that gravity would act as a decelerating force to slow that expansion down. However, what we really find when we do a very careful observation is that that expansion is accelerating. It's speeding up. And that result is completely unexpected. It's as bizarre as if suddenly one day gravity just stopped working around us.
Even though scientists are baffled, they know that dark energy makes up 70% of what's out there in the cosmos. So finding the answer to this great mystery has become science's holy grail.
Nothing excites a scientist more than something we don't understand, because that means there's a mystery still left out there to solve. And so, dark energy is sort of the mystery du jour.
Dark energy isn't just mysterious, it's also got a menacing side. If this acceleration continues, some scientists suspect our Milky Way could tear apart. Planets in the solar system would fly away from the sun, and it might get much worse. Everything in the universe could be ripped apart.
If you just expand space-time too quickly, you get dragged along with it, and literally you could rip apart the planets, you could rip apart the molecules, and even the atoms, until you just get this sort of a uniform sea of the finest paste of subatomic particle that can't get ripped down to anything more fundamental in a universe that just accelerates out beyond imagination.
Fortunately, scientists estimate it would be at least 20 billion years before this apocalyptic end. To unravel the mystery of dark energy and what fate it may hold for the universe, astronomers are using this, the Very Large Array, or VLA.
The VLA is the biggest, most flexible, and most sensitive radio telescope on the Earth. For this array, there's 27 antennas. Each of the 27 antennas is 25 meters in diameter, about 82 feet. The antennas are over 200 tons each. This array is designed to make images of anything that emits radio waves in the distant universe.
So far, it's been impossible to detect dark energy directly, but the VLA is trying to track its effect on everything else out there.
We can use these telescopes to get very high-resolution images of objects. If we can get a distance to an object and we can measure the speed at which that object is receding from us, then we get a very good and precise measurement of the expansion rate of the universe.
But there's other, more important reasons for solving this cosmic puzzle.
Who knows? It could be a clue to really understanding how all the laws of physics come together.
We are on the verge of a revolution in physics, and we don't really have these sorts of revolutions very often. Modern physics is responsible for quite a number of the things that we're used to in our everyday life, from the lasers used in eye surgery to the big screen televisions that we have at home. These all came about from basic research in modern physics. And what we have now is an opportunity to understand something new about the universe.
The enormous power of the Big Bang unleashed forces that nearly 14 billion years later continue to rule the universe. In a single instant, the Big Bang laid the foundation for every explosion since. The universe is a place of frightening power. The energies unleashed on our planet by earthquakes, hurricanes, and volcanoes pale in comparison to the forces at work in our explosive universe. Forces of unbelievable strength and intensity that could in an instant extinguish life on our planet. From exploding stars to colliding asteroids, we're at the mercy of immense powers we only barely understand. It's a fast-paced world, and in it, we lead rapid-fire lives. Everything's rush, rush, rush. From the 20-minute workout to the 2-minute burrito. Faster is always better. But we're going to show you a whole new side to speed and what it means in a universe that's ruled by it. We'll start with the fast and go even faster. From the rockets and spacecraft that speed us through space to the new engines scientists are working on that'll take us faster than we've ever gone before. We'll explore how immense speed alters the very fabric of space and time, and end with the science that's imagining things that seem straight out of science fiction. Black holes, warp drives, and tunnels through space. But before we get to all that, let's start with what we know about speed and what we think of as fast. Our fastest Olympic sprinters max out on the track at just under 28 miles an hour. At full gallop, a quarter horse can hit the wire going close to 50 miles an hour. A stock car tops out at around 240. A fighter jet can hit speeds of 1,000 miles an hour. The space shuttle circles Earth at about 17,000 miles an hour. And the fastest man-made object ever to be rocketed into space? The New Horizons probe, which is speeding towards Pluto at 52,000 miles an hour. But it's still going to take New Horizons 9 years to get to Pluto. That's because the distances in our solar system are enormous. For a little perspective, take a fast car and a speed we can understand, like 100 miles per hour. Physics professor Lou Bloomfield will show us just how far that would get us joyriding around the solar system.
Even in a fast car like this Lamborghini, it takes a while to get anywhere. If you were to drive across the United States at 100 miles an hour, it would still take you about 30 hours to complete the journey. Suppose you wanted to go to the moon. Now, you'd be traveling at 100 miles an hour for about 14 weeks. And what if you went to Neptune? Neptune, the last planet. Well, you're talking about 3,100 years at 100 miles an hour. So if you'd started when Socrates was a kid, you'd still have maybe 500 or 600 years left. Long trip. That's because in this universe, the distances are truly enormous, and 100 miles an hour is nothing. You need something a lot faster. Like light. Nothing is faster than light.
The speed of light. Nothing in the known universe travels faster than light.
The speed of light, that's the ultimate speed limit, 186,000 miles per second.
186,000 miles per second. That's 670 million miles an hour. That's fast. But how fast? How many times could a beam of light cover the 2,500 or so miles between New York and Los Angeles? Well, in just 1 second, that beam would travel back and forth nearly 75 times. But even with its tremendous speed, light still takes time to travel from one point to another. For a little context, here's Caltech astronomer Robert Hurt.
So to get an idea of just how fast light really travels at 186,000 miles a second, if we were to take this mirror and flash a pulse of light between here and the moon, it would take over 2 seconds to make just one round trip. And light from the sun, it's already 8 minutes old by the time it reaches us.
While light may move fast, it still takes time for it to travel through space. Sometimes, a great deal of time.
The sun is far enough away that the light which left the sun about 8 minutes ago is just arriving here on Earth now. Galaxies are so big that even though light is traveling at 180,000 miles per second, it takes a long time to travel from one side of the galaxy to the other.
Given that it takes light significant amounts of time to travel through the vastness of space, light speed isn't like what we see in the movies.
In your science fiction view of what it's like to travel the speed of light, you're sitting in your spaceship and you press the light speed button. And the stars start to zoom past you at incredible speeds. Well, if you really were going at the speed of light and you were looking around you, here's what it would look like. The stars don't move, and you think, oh, did I do something wrong? Do we have to get Harrison Ford in here to fix it or something? And no, they're moving a little bit.
The stars don't zoom by in a blur, because every single one of them is so far away. So far that even at light speed, it takes years to get to the closest one. And the farther away the object is, the longer it takes its light to reach us. In fact, everything outside our solar system is light years away. And a light year is about 6 trillion miles.
The nearest stars are years away, the nearest galaxies are millions of years away, and the universe is much bigger still.
So big, in fact, that whenever we look into the night sky, we're looking into the past.
When you look at a star in the sky, you're actually looking at the way it was back in time, hundreds or thousands of years ago, because it's taken that long for the light to reach us.
When a star explodes 5 billion light years away, it takes the light from that explosion 5 billion years to reach us. It means that that star exploded before the Earth even formed 4.7 billion years ago. But only now is that light reaching our telescopes, allowing scientists to study how our universe has developed.
If you look at a distant galaxy, you might be seeing that galaxy the way it was billions of years ago. We could be observing dead galaxies which just haven't had time for the light to reach us yet.
Nothing's faster than light, but even it takes billions of years to travel across the cosmic expanse. So even though we're always pushing the envelope to go faster and faster, our speeds don't even dent distances in space. If we ever hope to explore the far reaches of our solar system and beyond, we'll have to develop new technologies and figure out new ways to get there. Space exploration depends on speed. The faster we travel out here, the more we can learn. It was speed that got our astronauts safely to the moon. And it's speed that's gotten our spacecraft to Mars. But even with great speed, the distances between the planets are so great, it still takes years to reach them.
If we really want to start to get out to the outer planets and not take years or decades to do so, we need spacecraft that can go increasingly fast, that really can have more speed than what we manage today.
The technology that launched us into the space age decades ago is, for the most part, the same as we use today. These rockets burn fuel to push them up through the atmosphere to space.
You have to burn fuel to speed it up to get it away from the Earth. And that means you have to burn a lot of fuel.
Booster officer confirms a good solid rocket booster separation.
The fuel needed to get the space shuttle into orbit weighs 20 times more than the shuttle itself.
Atlantis, go at throttle up. Atlantis copies, go at throttle up.
That's more than 3 million pounds of fuel just to get the shuttle a few hundred miles up to orbit Earth. Now imagine how much fuel you'd need to send a spacecraft millions, even billions of miles from Earth.
We can't carry enough fuel in those rockets to make any voyage because all of our mass would be in the fuel and we'd have nothing for the spacecraft.
We've gotten spacecraft to the outer solar system before, but it's taken as long as a decade. And we've done it without burning much fuel at all. How have we achieved that? We use the planets themselves for something called a gravity assist.
The gravity of the planet reaches out and grabs the spacecraft, and as the spacecraft comes by the moving planet, the planet speeds up the spacecraft and sends it out to the outer solar system.
Gravity assist is really about trading momentum. As the spacecraft edges past the planet passes on some of its momentum, which is translated into speed. What happens out there in space is pretty much the same as what happens here on the roller derby rink. Looking for a boost, the smaller skater approaches the larger skater from behind. They lock hands, and in the process, the larger skater transfers some of her momentum to the smaller one and catapults her out at a faster speed. The same thing happens in space. The planet's gravity reaches out to lock hands with the spacecraft and throws it out at a greater velocity. Gravity assists can add a lot of speed to a passing spacecraft. The planet Jupiter helped accelerate the New Horizons space probe an additional 9,000 miles an hour and trimmed 3 years off its trip to Pluto.
This is a game of cosmic billiards. And scientists are really good at this. It saves us a tremendous amount of fuel when we're going to the outer solar system.
But gravity assists have limits. The planets need to be aligned correctly for them to work and make the trip as short as possible. On top of that, gravity assists can't accelerate spacecraft fast enough to make trips through the solar system routine. After all, it's still going to take New Horizons almost a decade to travel to Pluto. To get them out there faster, we're going to need new technologies. Like the solar sail, it turns sunshine into speed. It works just like a sailboat, but instead of wind, the solar sail collects tiny particles of light called photons that stream from the sun.
The energy of the sunlight is pure energy. There's no mass of particles there. It's pure energy. When that hits something, you transfer the momentum from the photon to whatever you're hitting.
But only a tiny amount is transferred. And because there's no friction in space to slow the craft down, those tiny amounts build on one another to incrementally generate speeds of several 100,000 miles an hour.
We could get to Pluto instead of in 10 years like we're doing now. We could probably get to Pluto in 2 years with a solar sail.
If we can get probes like the solar sail into space, we'll be able to reach the kind of speeds that will help us study the far reaches of our solar system. But what about sending a manned spacecraft further than we've ever gone before? How fast would we need to go if we wanted to send astronauts to Mars?
It's possible to get to Mars with a chemical-only approach, but it is not very practical.
It's not practical because it takes so much fuel just to get us up into space.
The analogy is the analogy of a car. When you get going in a car, you start in first gear. You need a low gear to get going. And that's what the chemical rocket brings to you.
First gear in the space shuttle takes it from 0 to 17,500 miles an hour in 8.5 minutes flat. On its climb through the atmosphere, those boosters on the side are burning 10 tons of fuel a second.
It's that kind of power that's needed to accelerate the space shuttle to 17,500 miles per hour very quickly. Within 2 minutes, all of the energy is released from the solid rocket boosters, and then they're thrown away, which is very similar to a first gear and a transmission of a car. The space shuttle main engines are then releasing, for another 6 minutes, release all the energy that's stored in the hydrogen and oxygen, the propellant that's in the external tank. And so all of the propellant that's on the space shuttle is used up within 8 minutes.
And when the engines finally shut off, the shuttles consume nearly 1,500 tons of fuel.
Once you get to Earth orbit, you achieve orbital velocity of about 17,500 miles per hour, and then there's no more propulsion needed to stay in low Earth orbit. If you want to leave low Earth orbit, going to another planet, another more efficient use of the propellant is needed, which would be similar to third, fourth, fifth gear in your transmission.
And those who know space think it's time we take exploration into overdrive. And this former astronaut is ready to do just that. No one's been to space more than former astronaut Franklin Chang Diaz. He's logged more than 1,600 hours on his 7 flights aboard the space shuttle.
If you want to go to Mars, it'll take you today about 8 months with a chemical rocket. Such a mission would be highly dangerous.
Dangerous because once beyond the Earth's protective magnetic field, the astronauts would be bombarded with deadly, high-energy radiation.
In space, you need to give astronauts a fighting chance.
And for Chang Diaz, that fighting chance means speed. Lots of it. Chang Diaz is working on a new engine that could hurtle us through space at hundreds of thousands of miles an hour. It's called the magnetoplasma rocket.
Any rocket works on the principle of action and reaction. You shoot material at one end, you get pushed in the other direction by the action of the material leaving.
Diaz's rocket funnels superheated plasma through magnets to produce thrust. And thrust means speed.
What makes it go very fast is because it's so hot. The particles inside a gas or a plasma, in our case, are moving very fast. The magnetic field aligns these particles so that their movement is all going in the same direction. And that gives you the rocket that you want.
Because the plasma's so hot, the atoms are moving at tremendous speed. The magnets in the engine align those speeding atoms and shoot them out to create thrust. So much thrust that with the magnetoplasma rocket, Chang Diaz thinks we could make trips to planets like Mars routine.
With this technology, we could get to Mars as fast as 39 days.
But for now, the magnetoplasma rocket remains in development. Chang Diaz hopes to have it ready for testing in space by 2011.
Our first test will be done on the International Space Station. Things will happen very quickly after that. I think that person that is going to walk on Mars is already alive somewhere. Hopefully he's here in our team.
Even though humans are running faster, cars are racing faster, and computers are processing faster, we're still using the same propulsion power from decades ago. And since speed's key to our exploration of space, it's up to scientists to find new ways to go fast. Space exploration hinges on our ability to move fast. Even with our fastest space probes, it takes years to reach planets like Jupiter and Saturn. But what if we could harness immense speeds? Speeds that would cut the travel time to the planets from years to hours. Turns out, the faster you travel through the cosmos, the stranger it becomes. We used to think that time and space never changed. They were unbending absolutes. No matter where you were in the universe or what you were doing, a second would always be a second, and a mile would always be a mile.
For all of us in our everyday life, we still have space and time as two separate entities. You know where you are, and you look at your watch and you know what time it is, and they're completely separate things.
But they're not. Albert Einstein was the one who showed us space and time were two parts of the same thing. a four-dimensional fabric he called space-time.
Space-time is an intimidating word, but it's just a way of saying the universe. So if you want to meet somebody for a cup of coffee, the point is that you need to give them 4 numbers. You need to give them 3 points to locate you in space, latitude, longitude, and height above ground. But you also have to say when you're going to meet them there, or it doesn't do you any good. So the point is you need 4 different numbers, and we can think of those 4 numbers as the 4 dimensions of space-time.
And this four-dimensional fabric of space and time can change.
Before Einstein, we thought that space was absolute. No matter how you moved, space would be the same, distance would be the same, and time would be the same. After Einstein, we discovered that the speed was the most important thing in the universe.
Not just any speed, but the speed of light. 186,000 miles a second. It never changes, no matter what. It's completely different to what we know and experience here on Earth. If you're traveling in a car going 50 miles an hour and another car comes toward you at 50 miles an hour, you'll see that car passing you at 100 miles an hour. 50 plus 50 equals 100. Likewise, if you're going 50 and another car comes up behind you going 60 miles an hour, you'll see that car passing you at 10 miles an hour. So why do we see these cars going by us at speeds different from what they're actually traveling? It's because they're moving relative to us. Makes sense, but that's not how light works. Travel toward a beam of light at 500,000 miles an hour, and you'll still see that light passing you at 186,000 miles a second. Travel at 99% the speed of light, and light will still pass you at 186,000 miles a second. Light doesn't seem to know if you're moving or not, so no matter which direction you're traveling or how fast, its speed remains the same. And if the speed of light never changes, then time and space have to. Why? Well, speed is a measure of distance over time. And if 2 people, one sitting still and the other moving, both clock the speed of light the same, then something has to give. And that something is time. In order for both to see light moving at 186,000 miles a second, each must be experiencing time differently. That's Einstein's theory of special relativity.
This stuff is just mind-boggling, and that's the way it is. And so you have to retrain your boggle point, if you will.
Okay, so let's retrain. How does speed affect time? Well, thankfully, Caltech physicist Sean Carroll's got an explanation.
One of the fascinating things you would notice if you saw something moving close to the speed of light is that time on that thing would appear to slow down from your point of view. So to show you that, we have here a light clock. This is just 2 sets of mirrors, and light is bouncing back and forth in between the mirrors. Now, light is very fast. You wouldn't see the light going back and forth, so we've slowed it down. And all it's doing is ticking off time. But what would you see if I take this light clock and I'm moving with respect to you? What you would see is that the distance the light pulse has to travel between the 2 mirrors is now longer. But the speed of light is always the speed of light. The speed of light is the same to all observers. So how can that be reconciled? The answer is that to you, time seems to be moving more slowly. I always see 1 second per second as I am moving along with the clock, but you see time travel more slowly for me than it does for you.
Let's get this straight. The theory of special relativity explains how speed makes time relative to whoever's watching the clock. If you were holding the light clock, regardless of whether you're standing still or moving near the speed of light, you'd see that light clock ticking off the seconds at the same rate. But if someone watched you zip past them, they'd see the light clock ticking off those seconds slower. Because the speed of light is constant, time is relative to the observer. The theory of special relativity. And relativity isn't just a theory we ponder. It's actually something we deal with on a daily basis.
It really does happen. And we see the effects of this in everyday life.
How? Ever use a global positioning system?
Clocks measure time. With 2 clocks to measure a time interval and a radio signal traveling at the speed of light, I can measure distance. In my hand is a GPS unit I use to find out where I am at the surface of the Earth. In orbit, there are satellites with clocks on board. Using their clocks and my clock, I can find the distance to that satellite.
The signal from the GPS device travels at the speed of light to a satellite in space. The satellite measures how long the signal took to reach it to determine the distance.
It's almost as if I had a string stretched from me to that satellite. By doing this with 3 satellites at the same time, it's like having 3 strings stretched from the satellites down to the surface of the Earth. And where those strings meet define one place on the surface of the Earth.
But this triangulation depends on time, very precise measurements of time. The satellites calculate distance by comparing the time the signal left the Earth to the time it arrived. But because they're speeding around the planet at 7,000 miles an hour, the clocks on those satellites count the seconds differently than the ones on Earth. So we have to correct for that, and we do that by setting the satellite clock wrong.
We misadjust them on the surface of the Earth before we launch them, so that when they get to this funny orbit where they're zipping around, they're going the right rate from our point of view here on Earth.
And what if we didn't correct for the effects of relativity? Well, GPS would be useless.
If we didn't correct the clocks, our position would be in error by 7 miles a day, and a lot of people would be getting lost.
Relativity affects everything orbiting the Earth, even the astronauts in space.
The astronauts who spent time on the International Space Station for any amount of time come back to Earth a little bit younger than they would have been had they spent that same amount of time on Earth.
But only by a tiny amount. To slow the process of aging, you'd have to travel near the speed of light.
If you're going at 99.9% the speed of light, say you take a journey that for you seems to last for 20 years. You'll come back thousands of years in the future.
In the known universe, speed is what counts. But understanding speed and what it does to the universe turns our brains in knots. One thing is for certain. Speed opens the door to a cosmos that's different than we would have ever imagined.
Engine ignition. 4, 3, 2, 1.
The universe is a place governed by speed. Einstein showed us how speed altered space and time, which offered us a glimpse of a universe stranger than we ever thought. A universe where speed rules all. Einstein's theory of special relativity shows us how speed changes the very fabric of space and time. Near the speed of light, time slows to a crawl. Reach the speed of light, and time stops altogether.
Somebody like Einstein could look at the universe and say, nah, I think it must work this way, and come up with a whole new thing like general relativity, which was just out there.
The theory of general relativity. It's been called the greatest scientific insight in human history. General relativity built on the theory of special relativity and everything it said about speed to give science new insights on how the cosmos worked. And none of those insights were as revealing as what it said about gravity.
Gravity is a force that acts between any two objects that have mass. So basically anything that is physical matter has its own gravity field and reacts to a gravity field.
Gravity is what keeps everything here on Earth from floating away. Throw a ball in the air, and gravity pulls it back down. It's also what keeps all the planets in orbit around the sun. But for the longest time, no one knew how.
The difficulty was understanding how this could be. The Earth orbits the sun, of course. How does the Earth know the sun is there?
General relativity gave us the answer. Turns out it had everything to do with space-time. The fabric in which everything in the universe exists. And that anything with mass, like a star or a planet, warps it. Like a heavy ball sitting on a sheet of rubber.
Here in my front yard, I stretched a big piece of industrial rubber on a 2x4 frame to make a representation of a space-time continuum.
So what happens when you put something heavy in the middle of the rubber sheet?
Oh, it's really distorting the rubber, isn't it? Yes. If I look down below, oh yeah. That really curves space.
The sun, the Earth, or any other object in the cosmos does the same thing. They bend the fabric of space-time so that anything nearby that's smaller falls toward it.
Let's see what it does to the path of this mass as it travels through space-time. Here it comes. I'm getting trapped. Looks like I might be getting trapped into a black hole. I'm getting bent towards a heavy mass. Ah, space-time.
This warping of space-time explains why the moon orbits Earth, and the Earth orbits the sun. And it's the speed of their orbits that keeps the moon from falling into Earth, and the Earth from plunging toward the sun. General relativity gave us a greater understanding of gravity, but it also predicted something that seemed to come straight from the pages of a science fiction novel. It predicted the existence of objects so dense they tear the fabric of space-time. We call them black holes. A black hole is a supermassive object that creates a very large and very deep dimple in the space-time fabric. Black holes form when large amounts of matter are crammed into a very tiny space. To give you an idea of just how small, all the Earth's mass would have to be crammed into a space less than an inch across to turn into a black hole. In nature, though, Black holes are the ghostly remnants of supermassive stars that have gone supernova.
A black hole forms at the end of the life of a very massive star. And the whole core of the star goes bang like that in a fraction of a second. The force of that implosion is so great that the matter cannot stop itself and it falls into a black hole.
The closer you get to a black hole, the faster you have to go to stay in orbit. And in fact, when you get close enough to a black hole, there's no speed that is fast enough to keep you in orbit. And when you reach the point where even traveling the speed of light does not let you escape the black hole, that's called the event horizon.
The event horizon is where gravity's pull is so strong that no speed, not even the speed of light, can keep you in orbit.
Amazingly enough, even light is affected by gravity. If I take a flashlight here and I shine it around a black hole, watch what happens to the path of the light. Now, at first, when I'm far away from the black hole, light goes straight and true, as you don't expect. But as I sweep it into the vicinity of the black hole, it begins to bend. It's falling toward the black hole. It bends a little at first and then a whole lot. And finally, when I go right toward the black hole, the light just streams into it and is gone.
We've never actually seen a black hole, but scientists think they're at the center of every galaxy in the universe. They believe this because they see extreme energies moving at immense speed, pouring out from every galactic core, including ours.
We know that there are these massive black holes that exist in the center of galaxies. And the gravitational fields around these are so intense that material can get heated up to tremendous temperatures.
Scientists have also seen matter circling and then disappearing into what looks like empty space.
You can look out at distant objects where balls of gas seem to be orbiting in space around nothing. And then vanishing. So that's some of the best evidence ever for the existence of black holes.
General relativity shined a light on speed's role in the workings of our universe. And while it shook the foundations of physics, it's led to a greater understanding of the cosmos. It's predicted things like black holes and hints at the existence of a universe where truly strange things might be possible. In a universe so vast, is there any hope of us traveling fast enough so that we could visit the far-off realms of space? Will we ever be able to plant a flag in the most distant quadrants of the cosmos?
We are not going to achieve interstellar flight in our lifetime. We may be as far from reaching other stars as Leonardo da Vinci was from realizing an airplane. He had the idea, but it took another 400 years before that began flight.
Even so, it hasn't stopped scientists from imagining the theoretical possibilities of interstellar travel. One such possibility is a cosmic freak show, a much theorized portal through space called a wormhole.
So a wormhole is basically a thin tube of space that connects two very, very distant parts of space. So it's almost like a tunnel. It's a little part of space. You go in there and you pop out somewhere else in the universe.
A tunnel through space, a shortcut through the billions of light years separating the farthest ends of the universe. It begs the question of how anything could bore a hole through space.
A wormhole is basically like a tunnel through space itself that can connect one region to another region potentially very far away. So to illustrate that, we're taking space and imagining it as this two-dimensional sheet of paper. So we have a wormhole mouth that you can go in, and then the other end is a place you can go out. So you imagine a tunnel that goes into there and comes out of there. And you might say, well, it would take me longer to get from one place to another if I went through that tunnel than if I just took the direct route through ordinary space. But the point is that Einstein tells us that space and time are curved, they're flexible. So we can imagine picking up this piece of paper and curling these two regions so that they're close to each other. Then you go into that end of the wormhole, you come outside the other end, and there's a shortcut in between them in which the distance is not that much. So the wormhole provides a way that you can travel what appears to be a very long distance in a very short period of time.
And it's for that reason that wormholes have found a special place in science fiction.
If you want to write a science fiction novel, you might want to be able to get across the galaxy very quickly, and you don't want to be limited by the speed of light. So a wormhole can be a shortcut. It can be a way to get around all of the space that you have to travel through. If you believe that the speed of light really is a speed limit, you can't go faster than the speed of light, a wormhole provides you a way, maybe, to still go slower than the speed of light, but get to where you want to go much faster because the distance is much shorter. It's really just a shortcut through space itself.
A wormhole might also empty into another time. That's because wormholes are portals through the fabric of space and time. While they could theoretically link different locations in space, they could also theoretically link up different locations in time.
Because space and time are mixed up together, you could actually not only end up in a different part of space by going through the wormhole, but you could also end up in the past. You could end up in a different part of time. You could go into your own past and then come visit yourself before you entered the beginning of the wormhole.
So you could have a wormhole that goes from your living room to your dining room. They might be 5 years apart. So you enter one this year, and you come back 5 years ago. And if you take the paper with you, you've got some good chances of doing well in the stock exchange.
No one's ever seen a wormhole. The only evidence we have that they might exist is their presence doesn't violate any of our current theories about how the cosmos works.
So within Einstein's theory of general relativity, you can imagine a space-time that has a wormhole in it.
What's hard to imagine is how you create one.
It turns out to be very difficult to make one. You need to rip space apart to connect the two different parts.
The relativistic nature of space-time opens the doors to all kinds of possibilities, even if they're theoretical. Besides the wormhole, there's also the idea of collapsing space and moving it in order to cover tremendous distances.
If you were in a spaceship and you wanted to cover great distances, well, instead of hitting the throttle and going for max speed, why don't you just change the space? Create space behind you, expand it, and contract it in front so your space actually does the moving.
That's the theory behind something called the Alcubierre drive or warp drive.
The theory behind these drives is to try to cover great distances without going fast. Don't try to speed up within your local space. Make your space do the moving for you.
When we travel through space. But what if space moved instead of us? It's theoretically possible because Einstein's theory of general relativity tells us space-time, that fabric in which everything in the universe exists, can be turned, twisted, folded, and stretched. What a warp drive would do is collapse the space in front of it while stretching out the space behind it, allowing you to cross distances faster than the speed of light without even moving.
A good analogy is just a moving sidewalk. Then you climb on a moving sidewalk, and that's moving at 10 miles an hour in some direction. You personally think you're stationary, you're not moving compared to the sidewalk, but you see everything going by at 10 miles an hour.
But being theoretically possible doesn't mean warp drive is in any way practically possible. Though warping space is how it works, no one has the slightest idea what kind of machine you'd need to control the dimensions of the universe.
Warp drives. It's an interesting idea. Is it realistic? Is it ever going to happen? I doubt it, but it's a lot of fun to think about.
But did Da Vinci hear the same thing when he showed others his drawings of the winged glider? When it comes to crossing frontiers, naysayers are always in abundance. But they're not always right. Seems that whenever the imagination meets science, we perform the most amazing feats. Feats that take us farther and faster than we've ever gone before. Ours is a world ruled by speed. It's a high-octane existence where everything is go, go, go. That's just the side of speed we see in our everyday lives. But when we look closer, we see how speed reveals a cosmos where space and time aren't the absolutes we all think they are. Speed holds the keys to our understanding of the universe. And it's with speed that we'll be able to unravel some of our universe's greatest mysteries.